Let's start. Okay, so we started looking at fully differential op-amps, and fundamentally the big difference is that you need common mode feedback. We started looking at the single stage fully differential op-amp. Okay. And we found out some really nice techniques. So one of them was, so the common mode feedback op-amp would be a replica of your main op-amp. It would, right? So that the PMOS, the output of the common mode feedback op-amp would be biased at exactly the point you want your main op-amp to be biased at. Correct? Okay. And then we saw that now that particular common mode feedback loop looks like a two-stage op-amp, right? So we found that we had to do, we had to add an extra compensation capacitance in the feedback loop to make sure that is stable. Correct? Everybody remembers this? Okay. And we are, of course, so when you look at it in the differential picture, you actually have two CCs across each of M3, M4. So you have one here and one here, each of value CC by 2, right? Okay. And the other thing we saw last, I guess a couple of classes ago, another way to do common mode detection, right? Primarily we want VOP plus VOM by 2. So one way to do is using the resistor, but we know that the resistor changes the DC gain. So another way is to make sure the common mode feedback op-amp, you just split the one of the transistors into 2, right? Except this will work fine for small signals. If you have larger signals, it will be nonlinear. And we also saw the source follower. Somebody mentioned the source follower in class, so we also looked at this. And you can do this also, right? You can make sure, all you need to do is add a source follower in the other path also. Make sure that source follower is a replica of these two source followers, and you're good to go. Okay? Okay. So that is as far as single stage op-amps go. So single stage, fully differential op-amps, no problem. Okay? Now suppose you need to build a two-stage fully differential op-amp. Okay? What would that look like? So I'll draw the first stage. Okay, what else? What will the second stage look like? What will it look like? So this is the first stage. I mean, first stage can look the same as, so you had a normal two-stage op-amp with single-ended output. First stage was the same as same as that of a single-stage op-amp, just a differential pair with an active load. Okay. Second stage, we wanted a GM. The simplest GM we could think of was, we wanted a single-ended GM. Simplest GM we could think of was a common source amplifier, so we added that in that op-amp. In a fully differential case, what would you do? Of course, yeah, same thing. Just add two PMOSs on either side. Okay, these two will be connected. So M1, M2, M3, M4, M5, 6, M7 and M8. So let me call this these two currents I2. Okay. So the inputs are VIP and VIM. Where are outputs VOP and VOM? Okay, which is VOP, which is VOM? Correct? Left one is VOP with M5, the other one is VOM. Correct? Everybody sees that? Okay. What I'll do is I'll call this VOP1, I'll call this VOM1. Okay. So now what you have is, you have two stages, first stage and a second stage, both are fully differential. So now you have to add common mode feedback for both stages, not just the first stage alone or not just the second stage alone. Correct? You want to stabilize the common mode of both stages. Okay? Okay. How would you control? Okay, so let us see. You want to control VOP and VOM. How do you do it? How do you control? VOP1 and VOM1, the output of the first stage. Okay, so what do you do when you do common mode feedback? You want to find some particular parameter which affects the output common mode. Use the common mode feedback to set that, right? To control that somehow. That's what you do normally. That's what we did in the other case, right? Let's go back to the other case. Oh, it's completely messed up. Okay, so okay, if you look at the single stage, right? What did we find out? We want to stabilize VOP and VOM. What does VOP and VOM depend on? How do you change VOP and VOM? You can do two things. We looked at both, right? Both are there in this picture. If you change the drive of VSG of M3 and M4, that will change the output common mode. If you change the gate of the NMOS current source, that will also change the common mode. Correct? We said we could do both. You could either control apply the common mode feedback to this or apply the common mode feedback to this. We looked at both. Okay? Okay, so let's go back to this. What will affect VOM and VOM1 and VOP1? What? Sorry, who's that? I'm not able to. Oh, okay. Sorry. Okay. The gates of M4 and M7 and M8. No. I'm asking for VOP1 and VOM1. Right? I want to find out what is going to control VOP1 and VOM1. That's the output of the first stage. I want to control change the common mode. Which parameter will change the common mode? Current in which common source? Which common source? No. Can you name the transistor? M5 and M6. Really? Okay. So the thing is, if you change the VGS for a transistor, the current will change. Okay. But you can't say that changing the current is going to change the VGS, right? The effect is only one way, right? So you can't change I2 and say VSG is going to change. That is not going to happen. Okay. What else? Yes, Milan. Gate of 3, 4 and M0. Again, it's the same thing. This is just right? Same as a single stage op amp. So you can control either of these. Okay. So let us say I choose to do this. Let's say I do it and I'm going to control this. Okay. That's good. So we know one way to set the common mode of the first stage. What about VOP and VOM? M7 and M8. Okay. So that is one. So M7 and M8. Those, if you change the gates of those two, it will change the output common mode. Anything else? Absolutely. Everybody sees that? You change the common mode of the first stage, you change the common mode of the output also. Why is that? Remember, we discussed the pseudo differential amplifier. M5 and M6 pair is actually a pseudo differential amplifier. Do you remember this? This was 2 classes ago. Remember this case? We compared this to something like this, the fully differential case. So in the pseudo differential case, your sources are actually grounded. In this case, you have a PMOS pseudo differential amplifier. RL is just the output impedance of your current source, M7 and M8. Everybody sees that? Okay, so what is the major characteristic of your pseudo differential amplifier? It has common mode gain also, correct? Which is equal to the differential mode gain. So that is a fundamental reason why you can actually control the output common mode using VOM and VOP also. In other words, using for example M3, M4, gate of M3, M4. Correct? Okay. So we know 2 ways to control M5, M6. We know 2 ways to control, 2 ways to control VOP, VOM, and 2 ways to control VOP1, VOM1 common modes. Okay. So we'll start off with the first one where you do something. We'll do both separately. Then we'll see if there is a way to combine them together and do it. Okay. Okay. So I'm going to copy this, okay. Okay, so let's do the stage 1 first. Okay, I'm going to call this OTA 1. So I'll call that VCM ref 1. Okay? Huh? Oh, yeah, okay, so I'll just call it an opamp. Okay? Yeah, an OTA is an operational transconductance amplifier, but I'll just call it an opamp. Okay? In reality, that is actually a transconductance, right? Is that right? Isn't that right? A differential pair with an active load is actually a transconductance of value GM1. Right, that's why I called it OTA 1, but let's just call it opamp 1. So this is stage 1. Okay? So suppose I needed to stage 2. I would apply VOP plus VOM by 2 to this. We call this VCM ref to distinguish it from this. And let us say in this case, I choose to apply it here. Okay? Okay. So now, how would you choose VCM ref 1 and VCM ref 2? Let's start off with VCM ref 1. Actually, first of all, what about the signs of the op amp? Is it plus at the top, minus at the bottom, or the other way around? Let's start off with the first one. So VCM ref goes to plus or minus? VCM ref 1. Isn't that what we did here for the single stage op amp? This is basically a transconductor, right? What is this? you have apply a VD, the output current is GM times GM1 times VD. Correct? So at the end of the day, this is just a transconductor. Right? That's why I did it. You can look at it as an op amp, you can look at it as a transconductor. Okay? That's why I just drew it like a transconductor. In fact, I think we started off using an op amp, but we decided a single stage op amp, it's both an op amp and a transconductor. That's why I just put it that way. Okay? Well, see, remember in a single stage op amp, okay, so if you really want an op amp, you want the output impedance to be very low, right? In a single stage op amp, that's not necessarily true, right? So it is actually more like a transconductor. But there are certain applications where you can use it. For example, driving capacitive loads. If you drive resistive loads, that's a problem. Having a high output impedance is a problem. But if you drive capacitive loads, it's not a problem. We looked at this when we were looking at the single stage from the block level diagram. Everybody remembers that? Last month sometime we did it, right? If you for driving capacitive loads, this is fine. Okay, even if it has a large enough output impedance, that's fine. It's able to drive capacitive loads. It's only when driving resistive loads where the large output impedance becomes a problem. Correct? So, okay, the transconductor also has its own output impedance. What is the gain of that single stage op? Okay, in this case that that op amp happens to be a single stage op amp. That's what we did for the first stage. This happens to be a single stage op amp. What is the gain of the single stage op amp? It's GM1 times, okay, if we just look at this one, it will be GM of the NMOS times GDS of the NMOS and over GDS of NMOS plus GDS of PMOS. Right, that is the gain. So it is actually driving a voltage. Correct? I just drew it like this. Don't get confused by this. I can draw it like an op amp if you want. If you think won't confuse you. Okay? Okay, so signs. This is right? Okay, what about this one? Upper is positive, same thing. Okay? Okay, so that's for the signs. How about the values? Let's start off with VCM ref 1. What would you choose it as? Can it be anything? Can it be VDD by 2 for example? We have seen in the previous case you wanted to choose it as VDD by 2. Can you choose it as VDD by 2 here? You can't. Why not? Okay. Are you sure? What do you want the common mode at VOP1 and VOM1? VDD by 2? Is that right? VDD by 2 plus VT. Is that right? Yes, Amit. What do you think? Anup? VDD by 2. The VOP1 and VOM1. No, I am asking about, let's start off with VOP1 and VOM1. What do you want it to be biased at? VDD by 2 plus VT of? Does that sound right to you? Does that sound right to everyone? That's not correct. The answer is already here. Yes? Exactly. Right? You want it to be biased at VDD minus VSG5 at a current of I2. Right? You already want the output stage to be biased with a current of I2. So obviously VOP1 and VOMB1 has to be biased at VDD minus VSG at a current of I2. Okay. How do you generate this? So now you need VCM ref 1, which is that. How do you generate it? Huh? Another path in parallel. In what way? So tell me what to draw. This is VDD. What do you want me to draw here? Okay. A current mirror. PMOS, so you want me to draw PMOS here? Okay. So this is NMOS. Okay. What do you want me to do next? Diode connected which one? Diode connected what? Diode connected NMOS or the PMOS? PMOS. Okay. What else? This should be? Okay. And this should be what? WRL of 5? Will that work? Okay, yeah, this will work. This will work perfectly fine. But suppose if I2 is very large, you don't want to burn extra power. This is just burnt power. What do you do? Right? Back to the same old replica bias. Right? So all you have to do is make it 1 by n times I2 and 1 by n times the device size. Right? Then you automatically generate. Right? You already know what I2 needs to be. You have some current reference, so you can mirror it through the NMOS. Right? Okay. What about VCM ref? What should that be? VDD by 2, because there you want to maximize the swing, right? And you don't have any constraints like VOP1, VOM1. Approximately VDD by 2. Okay? Okay? How about the common mode detector? What would you use for stage 1? What would you use for stage 2? Resistive divider for what? For stage 1. Is that right? How about stage 2? Also resistive divider? So what are the pros and cons of the resistive divider versus the other one? Power. Power. What is the problem with power in either case? Somebody said something here. Low gain. Low gain from what? Because of? Right? You didn't want the resistive, adding a resistive divider would reduce your DC gain. Right? So that was the problem with the resistive divider. What was the problem with the other one? Correct? Linearity was the problem. Swing. If you have very large swings, it's not very linear. Okay? So think about those two things and tell me which one you would use. Where? This is a two-stage op-amp. Okay? Think back as to what the trade-offs were in the two stages. What did you require from the first stage? What did you want from the second? What did you want from the first stage? Stage 1 you wanted high DC gain. Right? That was fundamentally because stage 2 you could have some resistive loading at the output. You want to drive resistive loads. You want to make that up by having high DC gain from the first stage. So you don't want to add a resistive divider, resistive detector there and screw up the DC gain. Okay. So what do you use? You can use the other one, the other kind, right? Any of the other kinds where you split the other one. So that will come inside op-amp 1. Okay. Is linearity a problem? No, because you expect the output VOM and VOM1 and VOP1 to not swing as much as, let's say, the output VOP and VOM. Right? They may swing, but not as much. Right? So, what shall we call it? Okay, I'll just call it non-resistive. What about the second stage? Second stage, you would want to use resistive because you expect very large swings. You want it to be linear. You don't mind because your load might be resistive as well. So you don't mind if you use a resistive. Okay? Okay. So we have decided VCM ref. Okay, we have decided the common mode detector. What about the op-amps? Op-amp 1 and op-amp 2. What do you want? What are you going to use there? Normal single stage op-amp. That's what we did in the other case. Perfectly fine. Okay. Anything else? Any other difference? Would you use the same type of op-amp for both op-amp 1 and 2? So op-amp 1, that's what we did. What did we want from inside the op-amp? Yes, I think you said something about. Right? Op-amp 1 is the same as what we had for the single stage, the fully differential. What was that? It was just a replica of this one. So you have input NMOS pair, you have an input NMOS pair. The active load will just be a replica of M3, M4. That's what you wanted. So that's settled. Fine. What about op-amp 2? Op-amp 2, you'd want it to have a PMOS input pair, right? Because what you're driving, you want the NMOS active load to be replicas of M7 and M8. Everybody sees that? Because now you're controlling the NMOS current sources. Okay? Okay, so that is as far as the op-amp goes, the common mode feedback op-amps. Anything else we have missed out? Let's go back to this picture. Have we missed out anything else? Two important things we have missed out. Well, they're the same. Compensation. Okay, so where all do you need compensation? Gate and drain of M5 and M6. What is that for? What is this compensation for? This is just dominant pole compensation for your regular op-amp, differential op-amp behavior. Correct? That is just your overall op-amp. Okay? And of course, I have not shown it here. You can also have RC here. Okay? You can also have RCCC here. Zero, right? Zero cancellation, everything. Pole zero cancellation. Okay? Anything else? What do you see here? Nimidev, Rakshit. Compensation for the common mode feedback loop. We have not looked at that. Okay, where will you put that? You will have one here. And you will have one here. Correct? Remember, each common mode feedback loop looks like a two-stage op-amp. It has two stages. You will have to compensate it. Right? Is that clear to everyone? Okay. Okay, that was fairly straightforward, right? You just do each thing separately for each stage. Well and good. Yeah, you can decide that, right? Yeah, you tell me how what a phase margin affects. Settling time, right? You are worried about things like ringing, right? Settling time. If you make a phase margin too large, again it will take very long to settle. If you make a phase margin too small, it will start ringing. Eventually it will become unstable if your phase margin is less than 0. Okay? So settling time will decide how much phase margin you want. Typically you want at least 45, 60 would be a good phase margin. In most cases you would choose it to be 60 degrees. Okay? Okay? Let's go back to this guy. So we found that VOP and VOM are also affected by the gates of M3, M4. So let us say we do something like this. Okay? Everything else stays the same. Except the difference in this case is we are going to connect this to V bias. Right? Now M7, M8 are no longer controlled by your common mode feedback loop. Right? So we are going to put in a V bias here which will make this current I2 flow through the output stage. Okay? Okay, let me add this compensation cap just in case. But, so you are going to connect this to V bias such that it flows through, I2 flows through this. And you know that, so okay, first of all let's look at the signs. Does VCM ref go to the positive or negative input of the op amp? Of the common mode feedback op amp? Negative. Same as the previous case. Should go to the positive, right? Now you have a second stage in the common mode feedback loop, which is first M3 gives a negative gain through M3 and then another negative through M5. Correct? So it goes like this. Okay? So if let's assume that the common mode feedback loop settles, what will it settle to? It will settle to some VOM VOP1 such that the current of I2 flows through M5 and M6. Because at the end of the day what you are doing is you are still sensing VOP and VOM and feeding it back through the common mode feedback loop. And when it stabilizes, it will stabilize at a point where the current through M5 and M7 have to necessarily be equal to I2. Is that clear? Okay. What are the problems though with this? Do you see any problems? What is the difference between this case and the previous case? You had two what? What are the two controlling feedback? Oh, in the previous case. Yeah, in the previous case you had two separate loops, right? What happens in this case? M5, M6? You don't know the region in which M5, M6 are operating. Why not? What will VOM1 and VOP1 settle to? If the common mode feedback stabilizes, let's assume it stabilizes. If it stabilizes, what will VOM1 and VOP1 common modes be? VDD minus VSG5. Right? We know that VOM1, VOP1 can be controlled through the gates of M3, M4. And that is controlled by the common mode feedback loop. So once it settles, output will settle to VCM ref, which can be VDD by 2, same as before. VOM1, VOP1 will settle to VDD minus VSG5. Right? That is also fine. That is what you wanted in the earlier case also. Right? So that is also fine. So as far as the, the values of the voltages themselves are concerned, everything seems okay. How many stages do you have in this loop? How many gain stages? Right? You have 3 stages. So what is the problem? Stability. Fundamentally, actually so far we have seen only 2 stage op amps and 2 stages, right? Stability of 2 stages. So fundamentally you have to start worrying about stability a lot more than if you had just the other 2 feedback loops. Okay, so stability could be a problem. What else? So what will you do to improve stability? So fundamentally, this op amp doesn't need to have a lot of gain now. Correct? You don't need a lot of gain, and in fact you want to reduce the gain so that it becomes stable. Right? So you can actually make the op amp them NMOS pairs, input pair, with PMOS diode loads instead of active loads. So you can basically make it a gain of 1, right? Almost 1, approximately 1. So that way you will reduce the gain in the loop. Okay? Anything else? What else do you need for stability? We already had CC here for the differential compensation. What else? Do you need compensation capacitance for the common mode feedback loop? Where will you put it? Where will you put the compensation for the common mode feedback loop? CC right now as you have it, we had it before. Any 2-stage op amp has to have compensation on the second stage, right, for your differential mode gain. So where will you put the compensation for the common mode feedback loop? Gate and drain of M3, M4. Okay, so that is one option. Anything else? What else would you do? Drain of M5 and gate of M3. You want to put a capacitance between here and here. Is this a cascode? This is not a cascode at all. A cascade. Okay, so you will get larger Miller capacitance. Maybe. Okay, So if you go through the loop, right, if you go through the common mode feedback loop, what are the dominant capacitances as you have it right now? What is the dominant node right now? M3, M4? Well, I would think it's VOM1 and VOP1 because you have a huge Miller capacitance there already because you have compensated your differential mode, right? And that also appears in the common mode, right? So there is a possibility of making CC the common compensation capacitance for both the differential loop and the common mode loop because it is a common path. M5, M6 are common to both, correct? Okay, yeah, it is possible, but it will be quite difficult because what you have effectively done is to actually, so what will happen is either the differential mode or the common mode will be most probably be suboptimal. You are throwing too many things into the mix, trying to do everything with one single, even though it looks very elegant and everything. If you probably had to do it, you would try to do it the way you did here, because what does it do? It keeps things very clean. It separates the two common modes, right? You have separate compensation for differential mode and the two common modes. Area, power may be a little bit larger, right? But as far as most optimal design goes, this will probably be much better, right? You can trade off the parameters, especially like phase margin and so on. You can trade it off much better. Okay. Whereas if you're trying to do everything with one single loop, right, and one single compensation capacitance, plus the 3-stage in the common mode feedback, it is a tall order. It is possible, but it is a tall order. Okay. Okay. I think I wanted to cover a little bit more today, but let's just start, then we will continue in tomorrow's class. So fundamentally there is one last thing to finish up in op-amps, then we'll move on. Okay. The last thing we want to look at is something connected with this common mode feedback loop, which is 3-stage op-amps. So far we looked at single stage op-amps, we looked at 2-stage op-amps. We have not looked at 3-stage op-amps so far. This is the first time we are actually seeing 3 stages in a loop. Okay. So let us, I'll go to the next page. Right? Let us start off with this. What is VO? Do you remember this one? This is an ideal op-amp. You may remember this from 2 months ago. We arrived at a 2-stage op-amp with something like this, with a block diagram like this. Right, where you have a transconductor GM1. Actually, let me get rid of this. This is not GM2, sorry. Right, and you have an ideal op-amp, correct? What is the output voltage VO? Correct? This is what it is for the 2-stage op-amp. Okay, so what can you think of? So what we did is, we started off like this, we replaced that op-amp with a single stage op-amp, correct? What else can you think of replacing that with? What is a more ideal op-amp than a single stage op-amp? A 2-stage op-amp, right? So you can actually replace this second ideal op-amp with a 2-stage op-amp. Okay. It looks something like this. Correct? Okay, so what we'll do is so if this is C, there will be some C prime here. Fundamentally, this is your two-stage op-amp. So what we'll do is tomorrow's class we'll go ahead and analyze this, see what you'll find, right? What are the advantages, disadvantages of a three-stage op-amp? And that will probably be just enough for half the class. The other half we'll start off with a new topic. Okay, so we are going to cover two more topics. I think we have 12 classes. Yeah, I think we have 12 classes left. We'll cover, I'll start off with band gap references. Okay, after that we'll do output stages. Okay, so band gap reference is something, is a circuit. So what you want is, you want a bias voltage or a bias current, a DC voltage or a DC current, which is independent, hopefully, of process and temperature and so on, right, and voltage, right? And the voltage which is constant is the band gap, the silicon band gap. So you're trying to derive something based on that. Okay. The other thing is output stages, because we looked at the case in the 741 output stage. We didn't understand it fully at that time, we just let it go. So we're going to come back to those kind of stages and see what kind of, right, parameters are important to us in the output stage. Okay, so we'll start with that from Saturday most probably. Tomorrow we'll start off with band gaps. It will be a few classes of band gaps and then followed by your output stages. Okay, and a reminder, Saturday we have the exam from 5 to 6:30 or so in the evening. Okay, and okay, yesterday's exam. Okay, so